Very exciting to have Isil today. So Isil is a professor of computer science, UT Austin, and also co-founder of Veridise. It's a blockchain security company. And she's been a tremendous great work in the formal method and programming language. And today, she's going to talk about formal methods of zero-knowledge circuit programming.
Thank you so much, Dejun, for the kind introduction. So, as Dejun mentioned, I'm Isil Dillig. I'm a professor at UT Austin and also a co-founder of Veridise, which is a blockchain security company. And today it's my pleasure to tell you a little bit about our work on formal methods for zero-knowledge circuits. So first of all, I think everyone in this room, probably I'm sure everyone knows about zero-knowledge proofs, but in a nutshell, a zero-knowledge proof basically allows proving that some statement is true without revealing anything beyond the mere truth of that statement. And because of this nice property of zero-knowledge proofs, they've found many applications, as you all know, in the blockchain space, for example, in privacy-preserving financial transactions, ZK rollups, which are scalable layer 2 blockchain solutions, secure online voting, as well as many other application domains. But let's say you are a developer and you would like to incorporate a zero-knowledge proof into your application. How do you go about doing that? Typically, zero-knowledge proofs are implemented using these arithmetic circuits. So as you can see, so you basically have some inputs. You have these gates, addition and multiplication, and the circuit has some outputs. But the important thing here is that addition and multiplication happens in some modulo, some prime number. So you can essentially think of ZK circuits, as far as this talk is concerned, as a system of finite field equations, right? I'm going to represent the input variables of the circuit using X and the output variables Y. And in general, as you probably know, circuits also have some intermediate variables, but just to simplify things, I'm just gonna write a circuit as C of XY and kind of brush the intermediate variables under the rug to simplify things. Now, zero-knowledge circuits are very common, and there have emerged many different domain-specific languages that facilitate the implementation of zero-knowledge circuits. So, show of hands, how many of you are familiar with some of these languages? Okay, yeah. So there are a bunch of languages. In this talk, I'll primarily focus on Circom because a lot of our work has focused on Circom, but there are a variety of other languages like NARC from Consensus, Halo 2, and a variety of others. So now from the developer's perspective, here is how the general workflow occurs if you are trying to incorporate zero-knowledge proofs into your application. So first you pick your favorite domain-specific language and you implement the ZK circuit in your DSL of choice. And then at that point, the DSL compiler will do a lot of the heavy lifting. It takes this high-level circuit description and it compiles it down to some low-level constraint representation. So for example, R1CS or Plonk and so on. And then after that point, that's where all the kind of the crypto magic happens. And then, for what I refer to as a crypto compiler, this is not the main topic of this talk. But for the purposes of this talk, all we need to know is that after this low-level constraint, we basically get a prover and the verifier. And basically, the prover takes your secret information and it will generate a proof of the statement that you would like to establish. And then you can provide that proof to the verifier, which will either say, yes, this is a valid proof, or no, this proof looks invalid. Okay, so that's the general workflow we have in mind. Well, at this point, you might say, oh, look, this is great, right? All the hard work is already done for me. All I need to do is implement a ZK circuit. This seems very easy to, get zero-knowledge proofs integrated into my application. Now, that's true, right? All the cryptography system and the compiler does a lot of the hard work for you. But, the point I want to make is that you shouldn't be lulled into this false sense of security, even though a lot of the heavy lifting is being done for you, because it's entirely possible that your circuit is wrong, and as a result, you get a wrong prover and the verifier. And in particular, if the circuit that if the original circuit you implemented in your DSL has a bug, then what's going to end up happening is that the prover is going to end up proving a different statement than the one you intended, and similarly, the verifier is going to be trying to verify a different statement than you wanted to verify. But now at this point, this begs the question, Okay, I said you need to implement your circuit correctly, but what does it even mean for your circuit to be correct? I'm a formal methods person, and in formal methods, whenever we talk about correctness, it's always defined with respect to some specification, right? So ZK circuits is no different when we want to reason about the correctness of a circuit. It's also defined with respect to some specification. And in this context, the specification, you can think of it as it's the computation we want to certify. So in particular, I'm assuming that we're implementing a circuit that's intended to produce a proof that can certify that P of X is equal to Y, that you know the secret such that P of X produces Y. Basically, we define the correctness of the circuit with respect to a computation P, and the correctness of the circuit means that C of xy should evaluate to true if and only if P of X is equal to Y. So it's saying this constraint evaluates to true only for those input-output pairs that are feasible with respect to our computation, right? And if this criterion is met, then we say that the circuit is equivalent to our computation. But unfortunately, it turns out that many real-world circuits violate this property because writing circuits turns out to be very non-trivial. And in fact, at the startup I co-founded, Veridise, we do audit a lot of ZK circuits, and we always find more bugs in ZK circuits than other types of software like smart contracts or even blockchain implementations. And this is the case, even those ZK circuits are really developed by people who typically know what they're doing and what they're talking about. So based on this experience, I really believe that it's crucial to develop formal methods techniques that can be used to improve the security of zero-knowledge circuits, and this is what this talk is going to be all about.
So I'm curious. So, on the previous slide, can you say anything about the types of bugs that you would? So, was it the case that you'd have CXY equal 1 for multiple Ys with the same X? Was it that the
Okay, so Tim is asking a great question. What are the sources of bugs? And you will learn all about that in the next 5-10 minutes. Yes. Yes.
So
Kara.
you're focusing entirely on like the circuit layer, not compiling
Exactly.
down
There are
to it.
many kinds of bugs that are possible in different layers: the circuit layer, the integration layer, the DSL layer, the crypto implementation of the crypto system. But what this talk is focusing on is in the circuit layer itself. Exactly. So here's kind of a little outline for the rest of the talk. So I'm going to talk about two main projects. So in the first part of the talk, I'll tell you about a technique that allows us to verify an important property of ZK circuits, namely that they're deterministic. In the second part of the talk, I'll talk about new constraint solver support targeting ZK circuits, and finally, I'll conclude with telling you about some of the other work and talking about future directions. So let's start with the first part, which is proving determinism of ZK circuits. Okay, so to answer Tim's question, it turns out that a common reason why circuits are often not equivalent to the computation that they're meant to certify is because they are under constraint. So what do I mean by a circuit being under constraint? Well, it basically means that for the same input X, you can find two distinct outputs Y and Y prime, such that C of XY and C of XY prime both evaluate to true. Right, so basically it's saying for the same inputs, it evaluates the true for two distinct outputs. Now before we continue, let's pause here a second and think about why if a circuit is under constraint, that's likely to be a bug. So recall our definition of equivalence, right? So remember that equivalence says C should evaluate to true, C of XY should evaluate to true if and only if P of X is equal to Y. And this computation P that we're interested in is typically some deterministic computation, right? So basically, that means on a given input X, P can only produce a single Y. It shouldn't produce two distinct outputs, Y and Y prime. But if the circuit is under constraint, we know that C of XY evaluates to true for two different values of Y. So therefore, if it's under constraint and assuming that P is a deterministic piece of computation, if a circuit is under constraint, it cannot be equivalent to whatever computation it's trying to certify. So the moral of the story for us is that if a circuit is under constraint, that means it cannot satisfy any equivalence for any deterministic computation. So if we detect that the circuit is under constraint, then there's very likely to be a problem in your circuit. Now, of course, that said, there are some, this is not universally true. In some cases, the computation could be non-deterministic, but, in many cases, if a circuit is under constraint, this is very likely to be a vulnerability, and it's definitely something that you should give a second thought to and see if you really meant it to be non-deterministic. Okay, so I bet a lot of people at this point say if there's a notion of under constraint, well, can a circuit can also be over constrained? Sure, we can also, come up with a definition of an over constrained circuit, and intuitively, an over constrained circuit says that for some input that perhaps satisfies some precondition, there is no way to satisfy the circuit. So there exists an X such that for all Y, C of XY always evaluates to false. Now, are over-constrained circuits buggy? Yes, generally speaking, over-constrained circuits are also buggy, but they're typically not as bad as under-constrained ones. So if basically a circuit is over-constrained, in some sense it's too conservative, right? So it's basically, if you give it a valid proof, it might reject the valid proof. But if the circuit is under constraint, then that's a soundness rather than completeness issue, meaning that it may end up accepting proofs that it should not be accepting. It accepts valid proofs. So therefore, generally speaking, under-constrained circuits are a lot more problematic than over-constrained circuits. Yes?
So you talked about deterministic functions, but oftentimes, if you add the zero knowledge, then things are definitely randomized. The provers are randomized to be able to hide the witness.
So that's good question. What about randomization? That's usually encoded as part of the input of the circuit. Yeah, exactly. And by the way, I just want to make it clear that I'm not making this up. This is not just an academic problem. Under-constrained circuits are actually a real, cause of vulnerabilities in practice. And if you go and look, there are, like a bunch of vulnerabilities that are caused by circuits being under-constrained, and they can cause a bunch of headaches and result in serious issues like draining tokens from an account, double spending, and so on. And to give further evidence to this, there's actually a very nice empirical study paper that came out recently by Stefanos Chaliasos et al., where they basically did a large-scale empirical study of a bunch of known bugs in ZK circuits. And what they found is that 95% of all known bugs are actually due to the circuit being under-constrained. Okay, I think they looked at 99 problematic circuits in total, and 94 of them were due to under-constrained. One was over-constrained, and the rest were like neither over-constrained nor neither over nor under-constrained, but still not equivalent.
It's still hard to know how to interpret that, right? I mean, it could be the under-constrained ones are just much easier to find, right?
Over-constrained ones.
Sorry, no.
It is true. Over-constrained ones are actually easier to test
Okay.
for in general.
All right.
Yeah.
I was just wondering if there's like a sample bias in this statement at all.
Yeah, I'm not the author of the paper, but I will.
One of them's in the room, so I guess I could just ask
What's
Jens.
that?
Like, one of them is in the room. I could just ask him, I guess. So.
Oh, right.
Sorry, what was the question?
Oh, right. Okay, now I just realized the author
Could
of
that be
this
due
paper
to
is
sample
in there.
bias? Could it be that the reason that 95% of all known bugs in ZK circuits are due to unconstrained circuits is just because those are the ones that people happen to be able to find or have been looking for or something like that?
Right. I mean, I think there's definitely a bias. We debated for like a long time how to even classify them, right? And there's definitely some cases where it's kind of like ambiguous. So we try to outline as best as we can kind of like the methodology that we used objectively to kind of like classifying the circuits. And there's definitely also a sampling bias in the initial data set, right? So we kind of like went through all of the audit reports that we found and all of kind of like the bug recollection GitHub repositories that we found, which doesn't necessarily mean that this kind of like lists all the possibly observable bugs in general, right? Given that the space is also kind of like fairly nascent, right? It's a fairly preliminary study of kind of like what's going to happen still in kind of like the next 5 to 10 years, but I guess it raises a very important issue.
I guess what I'm curious to sort of close is there some heuristic story you can say about how these circuits get specified where you'd actually kind of expect the common error would be that they'd be under constrained?
Tim,
What do you mean? Could you repeat the question?
I think the question is like, what is there a basic story for why you would expect this? I think the classic story is like if your circuit is over constrained, then it will fail basic testing. Like the product won't
Exactly.
work, and
It's
you
much
won't- you
easier to
won't ship
test
it.
for.
Yeah.
Yeah, because you give it a valid proof, it's going to end up rejecting. So that's what I meant by it's easier to detect. But
Yeah.
under constrained circuits are, like by the time we get to look at them or they go, like they get released, they have not been found through
So
testing.
it should be 95% of all known bugs that survived
That
the
survived,
initial
exactly.
testing process.
Exactly, yeah, that's a good way of saying it.
whether a circuit is under constrained is also kind of like debatable because it kind of like depends on the specification of kind of like the what you
Okay.
actually want to prove, right?
But this is an
So
old.
is it okay if at this point I,
Please go.
take back over because
Exactly.
otherwise
Yeah,
we'll never
yeah,
be able
please.
to. I'll never be able to get through my talk in
Please.
the rest of the time. Okay. So hopefully I've convinced Tim and others in the audience that under constrained, circuits are an issue in practice. So based on this, we recently developed a new technique for determining whether a circuit is under constrained or not. And if you're interested in knowing more details, this was published at last year's PLDI. And we also have a tool that we built that we use called PICAS. So in the first part of the talk, I'm going to tell you about how this tool actually works. So before I tell you about how it works, let's first kind of set up a straw man solution because there's an obvious way to solve the problem. So recall that a circuit is under constrained. The definition is very simple. I can just write this one logical formula. It says you can find an X and two distinct outputs that both satisfy your circuit, right? Now this immediately suggests a very obvious way of solving the problem. So, as many of you who are formal methods, who've talked to formal methods people know, we love SMT solvers, right? We love automated theorem provers. So what we can do is you can take your circuit C, you can encode it as an SMT formula, for example, in the theory of integers or theory of finite fields. And you give this formula to the SMT solver, and if it says this formula is sat, that means your circuit is under constrained. If it says it's not sat, then that means it's properly constrained, or it means it's not under constraint. Well, that's the obvious solution, right? And trust me, that's obviously the first thing that we tried. But this is not a very practical thing to do because it simply doesn't scale. And why? Well, real-world ZK circuits tend to be pretty complicated things. They have, lots of, constraints. They have lots of, intermediate signals. There's lots of non-linearities. Everything is over finite fields. So if you, encode everything as an SMT formula and throw it at a solver, it will just choke and not be able to, even if you give it, a very long amount of time, it will not be able to terminate with an answer. So what we did instead is basically the idea underlying approach is to get a more scalable technique, but that combines SMT solving with a lighter weight static analysis technique. And here's the key intuition underlying our approach. So often you can look at parts of the circuit, you can kind of eyeball your circuit, and you can realize that some variable v prime, let's say, can be expressed as a mathematical function of some other variables v in the circuit by just doing kind of like a pattern matching approach. And if this is the case, if you can eyeball the circuit and realize that v prime is f of v, as long as you know that all of these v's are deterministic, then you can also conclude that v prime is also deterministic. So let me give you an example to illustrate what I mean. Okay, so here's a simple circuit that has an input x, an output y, and an intermediate signal z. So if you look at the first constraint, well, duh, right? Clearly z can be written as a mathematical function of x. And if you look at the second constraint, you also immediately see that y can be written as a function of x and z. But since we already know that z here is deterministic, that means y can also be expressed as a function of x. Okay, so therefore, just doing this kind of very lightweight reasoning, we can immediately conclude that the output variable is indeed deterministic. But in some cases, well, this is obvious in this case, but in other cases, it's not so obvious. So let me give you another example. So here we have a circuit with input x and three outputs y0 through y2. And these three constraints here basically say each yi is either 0 or 1, and it says that the input x is basically the sum of the yi scaled by 2 to the power I. Okay, so in this case, you can't just kind of look at the constraint and say, yeah, yi can be written as a function of x or not. Actually, let me ask you guys a question. I'll give you a moment to kind of stare at the circuit. Let's look at it for 30 seconds, and let's do a show of hands who thinks this circuit is properly constrained or under constrained. Okay. Who thinks this circuit looks good? Who says this circuit doesn't look good? Okay. So the issue here, whether the circuit is properly constrained or not, it depends on what finite field we're working in. It basically depends on kind of what the p-value is. So it turns out if p is less than or equal to 7, then this circuit is going to be under constrained, but as long as p is greater than 7, then it is in fact properly constrained. And to see why that's the case, let's consider what happens when p is 7 and x is 0. Well, clearly one possible satisfying assignment sets all of the outputs yi's to 0, right? Well, clearly that's satisfied because these say yi is either 0 or 1, and clearly if you sum up a bunch of zeros, you get 0 equals 0, right? If you look at the case where everything is 1, then again the bit constraints are satisfied, but now the key thing is that when we do the summation over integers, we get 7, but remember that everything is happening mod p, in this case p is 7, so therefore the summation will in fact evaluate to 0, so we get 0 equals 0, which is another satisfying assignment. The moral of the story is that in some cases, it's easy to kind of eyeball a circuit and say, yeah, this signal can be written as a mathematical function of another signal, but sometimes this is not so easy to do, okay? So our idea is basically to prove as many signals as possible to be deterministic by doing this lighter weight reasoning, and we only want to resort to constraint solving only for the non-obvious cases where we run out of other possible solutions. So this brings me to our technique, which is basically at a high level, you have this interactive loop between two components, namely the SMT solver approach and the static analysis approach. And these continuously exchange information with each other through a shared knowledge base. And what does this shared knowledge base contain? Well, it contains two types of things. So first, as Daejun was saying, range information turns out to be useful, so it will compute range information for all the signals. But most importantly, it basically has information about which signals have been proven to be deterministic. And if at any point in this loop, we find that the output variables are a subset of the deterministic variables in our knowledge base, that means the circuit is properly constrained. Otherwise, we're going to first resort to our static analysis because it's cheap, and we're going to try to infer as much range information as possible and try to prove as many variables to be deterministic as possible. And at some point, we will no longer be able to make progress using static analysis, and when that happens, we will hand things over to the SMT solver. And the SMT solver will kind of continue the work started by the static analyzer and try to prove more signals to be deterministic. But the good thing about this SMT solver is it can also potentially prove that an output signal is non-deterministic. And if that's the case, then if that happens, we can conclude that the circuit is buggy. But otherwise, we keep repeating this until we can no longer make progress. And if we didn't determine verified or buggy, we can also return unknown. And as you will see later, the unknown case will happen because of solver timeouts, right? Because when we make a query to the SMT solver, it may not be able to provide an answer in some cases. And the key point that I want to make here is that the SMT solver and the static analyzer play a complementary role each other in the sense that partial results from one phase can be useful to the other, as we will see shortly. So let me talk about these two components in a bit more detail. So the SMT-based reasoning takes as input our circuit C and a knowledge base KB, and it will either say verified or buggy, or if neither, it's going to at least return an updated knowledge base that can be picked up by the static analyzer. And what we do is basically here is, as you can imagine, we first generate a logical encoding of the knowledge base, everything that we know, encode it as a logical formula, and similarly encode the 2 copies of the circuit as a logical formula. So we have 1 copy of the circuit over output variables y, and another copy over a different set of output variables y prime. And note that they all share the same x because we're trying to reason about what happens if they have the same input x, can they have different outputs y and y prime. And then once we have this formula phi, we're gonna say for each signal s of c, we're going to check whether our formula implies s is equal to s prime. And again, s here is referring to the signal in the first copy and s prime in the other copy. And if that's the case, that means S is deterministic, so it's going to be added to our knowledge base. And similarly for each output, not for the intermediate signals, but for just the outputs, we're also going to see if phi implies S is not equal to S prime. And if that's the case, since S is an output, we definitely know there's a problem, and we're going to report a counterexample to the user. And the important thing to note here is that the stronger the knowledge base, in other words, the more information you have in your knowledge base, in general, the easier the query is going to be, because you can use the information in the knowledge base to essentially simplify your encoding of the circuit. So I didn't make it very explicit here, but when you know that some of the signals in the circuit are deterministic, you can use that information to basically eliminate some of those y primes in your second copy of the circuit, essentially. Okay?
Should I think of x here as fixed, or there's a for all x kind of?
So it's
going
an
on?
existential. So we're saying, does there exist a value of x? Yeah. So now let's turn our attention to the static analysis. And as I mentioned earlier, what we're trying to do is for each signal S in the circuit, we're trying to see if S can be expressed as a function of some other signals S1 through Sn. And if, according to our knowledge base, if we know that all of the SIs are deterministic, that means S must also be deterministic, so therefore S can also be added to the knowledge base. Now, here's the thing that I want to emphasize again, which is to note that the SMT solver and the static analyzer play a complementary role. And that is because we may not be able to prove some of these SIs to be deterministic using the static analysis alone, but we may be able to prove them using the SMT solver, so therefore they kind of support each other in the process. And to give you more of an idea of how the static analysis works, I'm not going to talk about the rules, but just to give you some idea. So we have inference rules that are written like this, and basically whatever is on like this side of the turnstile basically says we can prove that variable to be deterministic, and whatever is on the right side, the right-hand side, is the information we have available. So for example, delta is our range information, K are the signals that are known to be deterministic, and C is our circuit. And just to give you kind of like a sense, for example, we have this assign rule, which says that, let's say your constraint has an equation of the form C times X is equal to E, right? So this is syntactically one of the constraints in your circuit. And you know that C is a non-zero constant, and you've also proven E to be deterministic. From that, you can conclude that X is also deterministic. And if you're wondering, where are these coming from? Well, they basically reflect common patterns that we found in ZK circuits, and they're based on rules that are manually proven to be sound. So you can think of the static analysis here as essentially doing like pattern matching over a bunch of rules that have manually proven to be correct. And if you take our implementation and run it on a circuit, here is kind of to give you an idea of what it will look like. So how many of you here are familiar with Circom, one of the circuit languages? Okay. Anyway, for the purposes of this talk, you don't need to, be able to read Circom code. But so basically, as you can see, there's an input signal, there's an output signal, and there's some intermediate variables here. And as I highlighted here, the problem is the loop termination condition. Essentially, very classical error, right? There's an off by one error here. And because the developer forgot to, because it says I less than n minus 1 instead of I less than n, it happens that out of n minus 1 ends up being unconstrained here, even though it's supposed to be constrained. And if you take our tool and run it on this piece of code, the output will look something like this. So as you can see, it's saying a bunch of propagation. And this is where it's doing this kind of like pattern matching based static analysis. And it's able to prove some variables to be deterministic. And at some point, it invokes the SMT solver. And the SMT solver returns a counterexample. And as you can see, it says if you take in to be 2, and if you look at the last variables, I can, like make them different. So it's essentially giving us 2 different outputs that will satisfy the circuit. And of course, that's just one example. So to evaluate our approach, we did a larger scale study. So we gathered a benchmark suite from circumlib. So this is the standard library of the circum language. We looked at a total of 163 circuits. And these contain, on average, like 4,500 constraints and about 24 output signals. And the key result here is that we were able to provide a definitive answer for 70% of these circuits. So for 70%, we were either able to say verified or under constraint. And as expected, because circumlib is very widely used and you would expect most of these benchmarks to be verified. So out of those 101 circuits were verified, and 8 of them were reported to be under constraint, and they were in fact under constraint. This tool doesn't have false positives, so to speak. And if you're wondering were all of those buggy, yes, some of those correspond to bugs, but in other cases, we talked to developers, and I believe that in some cases they said we expected, the circuit to be constrained at the call site for efficiency reasons. For some of them, that was some of them were bugs, and in some cases they were not. Okay, so that concludes the first part of the talk. If you have any quick questions, I'm going to take a question or two.
Any quick insights? The circuit that failed, but by this tool. Any insights why?
Oh, that's because of the. So to repeat Dajan's question, why? So in the cases there are 30% of benchmarks where it can't produce an answer. SMT solver timeout. We ran it with, I forgot the exact time limit, but I think it was like 1 minute or something like that, but it was not able to say, it wasn't able to decide sat or unsat within that time frame. Yeah.
So I think you said both the static analyzer and the SMT side, they both contribute to the knowledge base, is that right?
Correct, yes. Okay. Yeah, exactly. Yep.
Do you have plans to include more operations like lookups, say, to this procedure?
Oh, like the lookup tables in the Halo 2 sense?
Yeah, yeah.
So if you look at the PLDI paper that I talked about, it doesn't talk about that, but we did some later work where we're working on like Halo 2 support. There's some basic support for lookup tables as well. All right, so in the second part of the talk, I'm going to change gears and try to address the question that Dajan was asking about. Like I said, there are 30% of these circuits, and even when we use a state-of-the-art SMT solver for finite fields, we get, we're not able to solve 30% of the benchmarks, and this is because of SMT solver timeouts. So the obvious question we asked is, can we do better? Can we develop a decision procedure for finite fields that works better than the state-of-the-art, at least for the types of practical queries that we care about? And that brings me to our new CAF paper, which talks about a new solver for finite fields based on the idea of split Grabner bases. And the key thing, I'm going to tell you more about how this works, but the key thing is that using our technique, you can actually do much better when you're trying to answer determinism queries. And in particular, compared to the prior state-of-the-art SMT solver, we can decide the satisfiability of 3 times as many queries within the same timeout compared to the previous state-of-the-art tool. So the rest of the talk is going to be how did we get this kind of improvement? What's the new decision procedure? So first, let me kind of, recap the problem that we're trying to solve. So remember, when we talk about SMT solvers, we're trying to decide satisfiability in some first-order theory. And in our case, the first-order theory that we're working with is prime-order finite fields, right? So in other words, we have constants 0 through p-1. We only have 2 operators, plus and times, and these are addition and multiplication modulo r prime p. And we only have a single predicate equality. And at this point, I do want to make a little remark. So if you remember the formulas that I was showing you for determinism, in general, they can contain disequalities, like when I wrote y is not equal to y prime. But for the, we can actually ignore disequalities because there's a way to get rid of disequalities and turn them into equalities by introducing more variables, but it won't, in a way that won't change the satisfiability of the formula. So we can pretend that we only have equality and ignore disequalities. And so the problem we have is, given a formula in a prime order finite field, is it satisfiable? And I'm going to assume that the formula only has conjunctions, because basically there's all this machinery around SMT solvers where you have the integration between the SAT solver and the first order theory solver, where all the Boolean structure like the disjunctions and so on, those are going to be handled by a SAT solver. So the theory solver can only focus on formulas that only have conjunctions.
Should I think of the SAT solver piece as just kind of easy, basically? Like that, the hard part is the SMT part, or?
It depends on the problem that you're working with. There are formulas where the Boolean structure can be challenging, but generally in this domain, it turns out to be the finite field arithmetic that's very challenging. So another thing I do want to point out here is, because the only predicate we have equality is equality, all of the formulas we have are of the form E is equal to E prime. And clearly we can write that as E minus E prime is equal to 0. And we have a conjunction of those, so that means we're basically interested in asking the question, given a set of polynomials, do these polynomials have common roots or not? Right? Does that make sense to everyone, this reformulation? So basically, if I give you the upshot here, is that if you take the problem of determining satisfiability, you can have an alternative characterization of it, which is that you're given a set of polynomials in FP, let's say over variables x, do these polynomials have common zeros or not? So that's, those are two equivalent characterizations of the problem. So this is kind of the alternative problem statement is how we're going to view things, but in order to kind of answer this question, we're going to need a little bit of background on algebraic geometry that's going to be very useful for answering this question. So the first important background is the notion of an ideal. Just to recap, basically, if I give you a set of polynomials S, the ideal that's generated by S is denoted using these brackets. And basically, it includes all polynomials that you can obtain by taking the polynomials in set S and multiplying them by arbitrary polynomials Pi, and then adding them up, right? So basically, any polynomial that can be written in this form is in our ideal. And the important thing for answering or for solving our problem is the following important fact, which is that if it turns out that 1 is in the ideal that's generated by S, then polynomials in S do not have common zeros, or in other words, that means the formula is unsatisfiable. So that's the basic thing that we're going to make use of. So kind of to recap, what that means is that if we have a way of proving that 1 is in the ideal, then that's 1 is in the ideal generated by S, that's great, then we have a proof that the formula is unsatisfiable. But then that begs the question, well, how do you check if 1 is in the ideal that's generated by S or not? So that's the ideal membership problem, right? For those of you who don't have background, well, it turns out that there's a nice way of doing this using the concept of a Gröbner basis. So basically, if you have given a set of polynomials, you can compute something called a Gröbner basis. And that's a very nice representation of the ideal that simplifies a bunch of computational problems. And it turns out that if you can compute a Gröbner basis for which there's an algorithm, then you can also answer this ideal membership problem. And this is exactly what the state-of-the-art, the prior state-of-the-art decision procedure does, right? So it first starts by computing a Gröbner basis. So given our set of polynomials S, it goes ahead and uses this well-known algorithm or one of its many variants called Buchberger's technique, and it computes a Gröbner basis of S. Then it does the ideal membership test, which can be done in linear time. So if 1 is in the ideal, it returns unsat. But here is the catch. If 1 is not in the ideal generated by B, This doesn't necessarily mean that the formula is set. This result only holds for algebraically closed fields, but finite fields are not algebraically closed. So therefore, in that case, if we cannot show that one is in the ideal, we do need to resort to backtracking search in order to try to explicitly construct a model. But even then, having a Grobner basis, you can utilize various nice properties of the Grobner basis to make backtracking search more tractable. So you can make it you can basically use properties of the Grobner basis to prune the search space. Okay, but here's the problem, right? So when I was talking about the previous algorithm, we said, hey, we can do the ideal membership thing in linear time. I was expecting one of you to ask, but what about computing the Grobner basis? Well, that's the bit that's sticky, right? Well, basically, in the worst case, Grobner basis computation can be doubly exponential in the number of variables. And unfortunately, so, if you're doing verification, usually if things are NP complete, we've learned to deal with them, right? Because SAT solvers are, that's the easiest problem for us, right? So we just basically say, okay, that's NP complete, not too bad. How does it work in practice? Well, unfortunately, in this context, for many problems of practical interest, computing a Grobner basis does end up being intractable. So in this work, what we ask is, well, can we at least avoid computing the full Grobner basis? Can you kind of compute it partially, do something so it doesn't blow up in our face? The answer turns out to be yes, at least for answering determinism, you can kind of get around computing the full Grobner basis. And here's the key observation that we made that kind of drove the entire technique. So if you look at the benchmarks where Grobner basis computation really blows up, these have a common pattern, right? They all turn out to require emulating bitwise reasoning using finite field equations. Okay, now I know what you guys are asking. Why the heck would you want to emulate bitwise reasoning using finite field equations? Well, we're stuck with them, right? If you're writing a ZK circuits, everything has to be expressed in terms of finite fields, so we don't have a choice. If you want to do bitwise reasoning, you somehow need to find a way of, emulating it using finite fields, right? And to kind of give you intuition about what I mean, so here is the constraint that we generate. In fact, it's very similar to the circuit that we looked at earlier, that you guys might have deja vu to that second example I was showing you earlier. So as you can see here, basically here we have a bunch of bit constraints that says yi is either 0 or 1, and we have what I call these bit sum constraints that say some variable can be written as the summation of yi to the power of y. Essentially, you're doing bit splitting in order to emulate bitwise reasoning using finite field equations. This is a very common pattern, at least, as I mentioned earlier, our primary language that we were looking at was Circom, so we mined a bunch of Circom projects, and we found that 98% of Circom projects have circuits that exhibit this pattern. Now, here's the important part. So it turns out that if I give you the entire constraint system, it turns out to be difficult to compute a full Grobner basis for the whole system. But you can compute it efficiently if you separate some parts of the constraint from the other. So in particular, if you isolate these bit sums from all the rest, along with the bit sums plus all the linear stuff versus all the other nonlinear stuff, then computing a Grobner basis for each of those in isolation turns out to be very practical. So that's kind of the intuition behind our approach. So we want to basically split the constraint system into multiple parts and compute Grobner bases for those separately, and then somehow iteratively refine them by exchanging relevant information. So that brings me to kind of the contribution of this CAV work, which is the idea of a split Grobner basis. And basically, so given a set of polynomials in our finite field, we say a split Grobner basis is a sequence of bases b1 through bn, such that each bi needs to be a Grobner basis for some subset si of s. So we split s into s1 through sn. We compute a Grobner basis bi for each of them separately, and we also require that if you look at the ideal generated by S, that needs to be equal to the ideal that's generated by the union of all of these bases, right? So, in other words, they kind of union up to our original basis, or our original ideal. And there's a trade-off here, right? So in general, if you can compute a full Grobner basis, as we will see, that contains more information. That's more useful, but it's harder to compute. There are problems where, the computation will blow up. On the other hand, the split Grosvenor basis is not as informative as the full Grosvenor basis, but hopefully we can split it up in such a way that will be easier to compute. So how do we use the split Grosvenor basis in our decision procedure? So the first obvious fact is that if we can prove that 1 isn't the ideal generated by any of those BIs, then that means some subset of the polynomials don't have common zeros, so therefore the full set of polynomials will clearly also not have common zeros, right? Because we're looking at a subset of those, right? So basically by doing this, by having a split Grosvenor basis, we can still determine in some cases whether the constraint system is satisfiable or not, or whether it's unsatisfiable. However, as I mentioned, it's not as informative because it could still be that even though 1 is not in the ideal generated by any BI, it could still be that 1 is in the ideal that's generated by S. So in this sense, it's not as informative. So what do we do? So it seems like this part seems a bit problematic, right? Because it seems like we're losing completeness. So how do we recover completeness? So recall what I said earlier. So even in the case where we compute the full Grosvenor basis, this doesn't give us a full decision procedure, right? Because we don't have that nice if and only if property. So even if we computed a full Grosvenor basis, we would still need to do some kind of backtracking search for model construction. So what? If we have a split Grosvenor basis, we do the same. We basically, if we cannot prove unsatisfiability using any individual basis, we're going to rely on backtracking search. And furthermore, we can still leverage the nice properties of each individual Grosvenor basis to help us to do the search. But as you can also imagine, when you have a split Grosvenor basis, the search algorithm itself gets more complicated, and it also, in general, can require more backtracking than if you had a full Grosvenor basis. So there's that trade-off. Now, in addition, what our technique does, additionally to reduce the reliance on search, it relies on information exchange between different bases. So it might give you this deja vu feeling like the first part of the talk where you were doing information exchange between the SMT solver and the static analyzer. And here we do something similar, right? So in this split Grosvenor basis approach, we break our system into n different subparts. We compute a Grosvenor basis for each of them separately. But after we compute a Grosvenor basis, we have this thing called the propagation module, which is going to kind of inspect each of the bases. And it's going to try to do some reasoning. If you added this, it probably, wouldn't make Grosvenor basis computation much harder, but it's potentially very useful. So it basically propagates these polynomials back and forth, and you can recompute the Grosvenor basis with those added polynomials. And the overall goal here is to construct a split Grosvenor basis that's almost as useful as the full Grosvenor basis, but that is hopefully much, much easier to compute than the full thing. So one thing you might notice is that this, what I described, is kind of a decision procedure, but at the same time not, because it doesn't specify, many kinds of details. For example, how do you split these polynomials? How does this propagation module work? And you can instantiate it in many ways, and it will still be sound and complete as we show in the paper. But the particular way in which we instantiate it is motivated by the observation I made earlier, which is that Grosvenor basis computation blows up when you have these bit splitting constraints. So in our specific instantiation of this algorithm, we separate the constraint into two parts. So we have the linear part, which does include the bit sums because those are linear, and we have everything else. And then the propagation module essentially focuses on inferring equalities based on bit sum congruence. So very tailored towards that observation I made at the beginning. And the key result is what I showed you at the very beginning. If you look at satisfiability queries about determinism, this technique makes a huge improvement. You can answer 3 times as many satisfiability queries as compared to the prior state of the art. But now you might ask, what about other types of benchmarks? What about those that don't involve determinism? And there the answer is mixed. It depends on whether you're an optimist or pessimist, whether you'll be happy about what I say. So If you're an optimist, it's good because it doesn't hurt anything. But if you're a pessimist, it doesn't make a big difference. So this technique is primarily good at, answering satisfiability queries that arise in the context of proving determinism, but it doesn't hurt anything else, so you might as well use it, right? So in the last few minutes that I have, I also wanted to tell you about some of the other stuff that we've been thinking about, and maybe some of you may be interested in collaborations. So when I think of formal methods, for me, the different tools we have come in a stack, and the most foundational tools in formal methods are solvers, like SMT solvers, SAT solvers, so those for like the layer 1 of the formal method stack. So once you have SMT solvers, then on top of those, you can build useful tools like verifiers and bug finders and symbolic execution tools. And then once you have verification tools, you can also do more advanced stuff like, synthesis. Can you, synthesize software that's correct by construction, or synthesize circuits that are correct by construction, and so on. I would say that this whole area of formal methods for ZK circuits, it's a pretty nascent field. So unsurprisingly, a lot of the work so far has focused on the bottom 2 layers. And I told you about some of the work that we did on solvers and verification, but we also have some additional work in the second layer that I also wanted to tell you a little bit about. So generally speaking, if I think of program analysis or verification techniques, like everything, there's always a trade-off, right? Everything comes in a big spectrum. So on one end of the spectrum, you have full-fledged verification techniques that come with very strong guarantees, right? You can say, I proved full functional correctness, but they tend to be pretty heavyweight. On the other end of the spectrum, you have things like bug finding tools that give very weak guarantees. So maybe they, say, they can have both false positives, they can also have false negatives, but their advantage often is that they're much lighter weight, right? So there's always a trade-off between different techniques. And the technique that I told you about in the first part of the talk, so I would say that falls somewhere in the middle. It focuses on a specific properties, in particular proving determinism, but it can at least, say, at least for the determinism property, it's verified, so it can give you some guarantees. So you might ask, well, what about other kind of alternatives in this design space? So we also build other tools that fall on different parts of the spectrum. So for example, in our recent Usenix 24 paper, we described a technique that constructs this graph abstraction of ZK circuits and does, analysis at the graph level. And that's a much faster technique. It doesn't require any SMT solver support, but it doesn't have any guarantees. It can have false positives, it can have false negatives. We also looked at the technique all the way on the other side of the spectrum. So we actually have this programming language for ZK circuits called CODA, and it uses a refinement type system, and then it basically, when it does type checking, it will output a bunch of Koch lemmas. So this technique is actually not fully automated. It can verify full functional correctness, but in the case where, the built-in Koch tactics fail, a person needs to go and prove those Koch lemmas by hand. So this is not fully automated. And there are a bunch of future directions that we're interested in exploring that some of them we already started on. Someone was asking about those. So one thing I'm very excited about is, like I said, a lot of our work has been focused on SERCOM and R1CS at the low-level representation. But there are constantly emerging DSLs for for implementing ZK circuits. So we're interested in building a verification-friendly intermediate representation for ZK circuits that can support many different languages like NARC, Halo 2, SERCOM, and others. Another thing that I'm very excited about is specialized solvers for integers plus finite fields. And why am I excited about that? Because if you want to prove equivalence between computation and the circuit, all the circuit constraints are in finite fields, but all the computation use integers. So if you want to, reason in an automated way about equivalence, then you definitely need good SMT solver support for theory of integers plus finite fields. And currently, we're also looking at more automated techniques that use SMT solvers for verifying equivalence between ZK circuits and the computation they encode that don't rely on manual proofs using Koch or Lean or some other interactive theorem prover. I wanted to acknowledge my collaborators. So you guys invited me to give the talk, but a lot of the work was actually done by others, not me. One of them is my PhD student, Shankara Pailur, who's supposed to defend in a week. I'm trying to convince him very hard to defend as soon as possible. Alex Özdemir from Stanford is a PhD student who's been collaborating with us. So he was the lead person on this finite field solver. And Alpier, who is a mathematician who was also one of the big brains behind the second part of the talk that I mentioned. So that's all I have. Thank you very much for inviting me.